So, hello everyone. Welcome back. Is there anyone coming in? Yeah, some people are still coming in. So, welcome back. As you can see, Gabriel Keller is finally here. That's yeah, so it gives me great pleasure to introduce Gabriele Keller as our opening speaker for ZuriHac 2022. Yeah. Gabrielle, she's a professor at Utrecht University, where she's been for 3 years. Before that, she was in Australia for I heard, 20 years. I was like, wow. And her interests include functional programming, but also formal verification. I guess that's also a topic that's close to many people's hearts here in the Haskell community. And when I asked her to come and speak, she gave me a choice of topics. So one was about accelerate, and the other one was formal verification. And she's like, you can choose. And I thought, I can't choose this. And then 2 months passed, and she said, I'm just going to give a talk on Accelerate. I said, okay, good. And so she's going to talk about Accelerate now. Thank you very much, Gabrielle.
Thank you. Thank you, Farhad, and thank you, everyone, for having me. Yes, I finally made it. I was planning to arrive yesterday, but Deutsche Bundesbahn didn't want me to. So as Farhad said, I used to work in Australia, and the Accelerate, what I'm talking about today, basically is a project that already started there. So lots of people have worked on it. Including Trevor McDonald, who came with me from Sydney to the Netherlands. And the main people who are working on this project at the moment are Trevor, Ivo, David, and Josh. And also lots of master thesis students, and some of the work I will mention today. So if I would ask around why you'll use functional programming, why you like Haskell, then probably things like that it's elegant, that it's readable, it's concise, maybe also laziness, expressive type system, maybe if you're interested in verification, things like that also, that it facilitates reasoning about programs, function as first-class objects, controlled side effects. Maybe all these things would come up and more. But one thing that probably would not come up as the major reason to use Haskell is performance. And not that it's necessarily a problem in all contexts, but it's kind of not the reason to switch to Haskell. And similarly, kind of array numerical programming, not probably the main, not the strong side of Haskell. So that was basically the motivation for Accelerate. We wanted to provide Haskell programmers with a convenient way to write high-performance code. And how can we do that? Well, like a lot of these features, I said, which are plus of Haskell in functional programming, the high-level abstraction, the conciseness, also come with a cost, and the compiler has to do a lot of work. But also, in the context of parallel programming, they can be an advantage because some patterns are basically more obvious and more easy to exploit. And we all have parallel hardware on our desktops and laptops. So the idea is to make it easy for Haskell programmers to exploit the hardware properly we have already, and to embed this programming language in Haskell, and then express parallelism basically via higher order operations on multidimensional arrays, so in a way which Haskell programmers already are used to program. We all like to use a lot of higher order functions and so on. And I want to start with the performance issues. So I will talk in the talk a bit about how we get to the performance, but you know, if you kind of install Accelerate, what can you expect? So if you look at more or less micro benchmarks, so kind of fairly straightforward little programs like matrix multiplication and so on. So on a single thread, if you don't exploit the parallel hardware, For sufficiently large data sets, it's comparable to C, faster if you then run it on multi-core on your GPU. And in general, basically, you get fairly good performance for dense data parallel computation, so it exploits the hardware pretty well. It has Achilles heels. So, for example, it is strictly functional, basically has a functional semantics, so there are no destructive updates of arrays, which if you do basically update the whole array, then it doesn't matter. But if your algorithm, if you basically, for example, have graph algorithms where you have a lot of sparse updates, then at the moment, this is not handled very well because we also internally don't use destructive updates yet. But that's one thing we're working on. Just to give you kind of two examples of a bit more complex benchmarks. So one benchmark Trevor implemented is the LULASH, the Livermore Unstructured Lagrangian Explicit Shock Hydrodynamics or hydrodynamic simulation. And the implementation, the reference CUDA implementation, which is optimized CUDA implementation, has about 3,000 lines of code. The OpenMP multi-core implementation has 2,400 because it's like already a bit higher abstraction level than CUDA. Accelerate has about 1,200, so it's a lot more concise, and of these remaining 1,200 lines of code, a lot of this is really the math you have to express basically in all of these languages in a pretty similar way. Now, we just ran the benchmarks again, so with a recent version of LLVM and CUDA, and for the CPU, we use the Ryzen Threadripper, and GPU and RTX 2080 Ti. And the performance is basically, so the CUDA reference implementation took 3.5 seconds, where Accelerate took 6, which is really annoying on old versions of CUDA. We were actually twice as fast as CUDA. The reason for that is, also old version of CUDA, but also on old GPUs. So one reason why we're now slower than the CUDA implementation is that the latest CUDA version has optimizations for more modern GPU architectures, and our code generation doesn't have that yet. So that's also on our to-do list, and I think we can beat them again. On OpenMP, we're also quite a bit faster. And you have to see basically both of CUDA and OpenMP are really optimized implementations. Another application we're working on at the moment is simulating basically formation of spatial patterns in ecosystems. So basically kind of the Turing pattern. So this is together with Johan van der Koppel from the Royal Netherlands Institute for Sea Research, and they basically study especially how salt marsh and things develop with the purpose of kind of figuring out what we can do to protect the coasts, because these ecosystems and these structures are very important for that. But yeah, so this is basically kind of Turing pattern simulation on a large scale, and this is kind of extremely time-consuming. So this is kind of the simple simulation where you just kind of, where we simulate the sediment and water flow rate for such a salt marsh ecosystem. And there, they gave us basically they had an implementation which was kind of Python Jupyter notebooks with calls to OpenCL. And I took that in, we wrote that in Haskell. So again, it's quite a bit more concise. And on the GeForce 1080, the OpenCL Python took about 1 1.6 seconds per frame, and accelerate was basically, without optimizing for it, basically straightforward accelerate quite a bit faster. So they're quite happy using it. So the main thing holding the problem we have with this project, or the thing where we have to do more work, is actually not on the performance side, but user interface. Like, Jupyter notebooks are really nice to use for researchers, like not computer science researchers, but people who want to do programming to get stuff done. So we're basically trying to spend, we're spending efforts on making it easier to use, because that's really more the pain point there. So how can you actually program in Accelerate? So let's start with, I'll just basically have a very simple example, just to give you an idea. If I want to implement in Haskell dot product, so a point-wise multiplication and the sum of two lists, I can use zip with and fold L. And because lists are not the fastest thing around necessarily, if I want to have that a bit faster, I can use, for example, unboxed vectors. So the code does not change much, or the code doesn't change at all. I just import a different library, and the type changes. Now, if I switch to Accelerate, the code changes a little bit, so that my fold L is now a fold. And the reason for that is those combinators are now parallel, and fold L and fold R have this inherent sequential execution, but this is basically a tree fold. So if you're not using an associate operator here, it's probably you won't get what you expect, but this way you have basically log-n parallelism here. Then the time constraint for unboxed vectors, we had unboxed. Here we have eld. That is basically just the type class of all the elements you can put in Accelerate arrays. What can we put in there? Well, what we would expect. Unit type, not exciting, but all the usual words, integer, types, float, double, character, bool. Then arbitrarily nested tuples of these types, user-defined types, but so basically, because we support regular data parallelism, we have multi-dimensional arrays, but not nested arrays. That means basically they are rectangular, so we don't have arrays which have as elements arrays of different sizes. If you need that, all the operations, fold, scan, come in a segmented version. So you can have a flat array and then segment information, and then these operations work on that. But you do have to do the management of the shape information and the data manually. And yeah, users can extend this eld class, and they can also, they're basically generic mappings from a surface type to efficient representation type. But if you're not happy with it, if you want to have a customized implementation, you can do that. Then if we look at the type of fold in particular in a bit more detail, we can see a bit more. So in addition to this eld constraint, on the element type, we have this shape type. And what you can see, what fold actually takes is not an array and returns a one-dimensional array and returns a scalar, but it returns an array of dimension n plus 1. So this shape is basically a SNOC list of the dimensions. And then it collapses the innermost or reduces the innermost dimension of that. And that happens in parallel for all the elements together. So shapes have this snug list form, and then the dimension 0 is basically here just Z. Scalar A is just a type synonym for an array of dimension 0, dimension 1 is a vector, and so on. But that means that my dot product actually has a more general type than I gave you initially. I said it reduces two vectors to a scalar. What it actually does, it takes two arrays of dimension n plus 1, pointwise multiplies them, and reduces the innermost dimension. So in some sense, this is basically the dot product is dot product, map of dot product, map and map of dot product, and you get the dimensionality in all, the parallelism in all dimensions. One thing basically I forgot to mention at the beginning of the talk, if you do have a question anytime, just raise your hand and ask. I'm happy to take questions at any time in the talk. Another thing we can do with the shape is we can use that to index into an array. So here in this two-dimensional array, we can get the fifth. We basically said A has the shape 5 times 2 is a two-dimensional arrays. And if we index to the position 2, 3, then we get 23. Also, we can take any kind of slices from the array in any dimension. So here, if we take this slice, then we get that sub-array. So it's a bit like if you, like in MATLAB or so, where you can do similar things with the slices. And so you can also use that to expand arrays in any dimension. So to summarize about what you can do, we have the usual kind of collection-oriented operations, maps, zip width, various flavors of scans and folds. So scans are really important in parallel computing. Then indexing, slicing, permutations. And with the indexing, if you just index, if you have a huge array, you index into the array, this array, then that's a single index is a sequential operation. So often you will do, if you want to index in a lot of elements at the same time, you do a back permutation. You can slice, segmented operations, which I mentioned. Then stencil operations, so basically maps, which take not only the current element, but a convolution matrix around this current element into account. And then kind of the most general thing, kind of a parallel for all. So generate gets a shape, and a function that maps an index to a value, and then produces an array of the given shape where each element in this new array is initialized according to this index to value function. While loops and iterations on the element and array level. And with this generate, you might realize that basically with a generate, you can implement a map, you can implement a zip width, you can implement stencil operations. So the generate is if the specialized operations don't do exactly what you want, then you can do almost anything with the generate. But you shouldn't, because if we don't kind of analyze the generate for particular patterns. So if you use a stencil operation, we already can see from the fact that you're using this operation what the communication patterns are and can optimize for that. But so generate is the fallback solution for it. So this means basically you have, if you have something like matrix-matrix multiplication, you can either kind of use generate here, where it's more or less a kind of for all loop where you take you multiply to two-dimensional matrices, and then you have this threefold nested loop. And by multiplying the corresponding indices of A and B, and then you sum, so you do fold plus over the resulting array. Another basically way to express this with higher order functions is you say sum zip width of the matrix of A, where you extend it basically one dimension, B the other dimension, so you create more or less 2 3-dimensional arrays, pairwise multiply that, and then reduce it. And you might think that the second one is pretty horrible because it has these huge intermediate arrays, but the code, the generated code uses basically, we use fusion very, very aggressively. So this also compiles to very tight loops without intermediate data structures. So you don't have to worry and accelerate that if you use these higher order combinators, that the memory consumption or memory access is too much. And if you think, well, seriously, I don't have to re-implement matrix multiplication again, I just want to call BLAS library, then you import the accelerate binding for the BLAS library and call that. Performance-wise, by the way, we're kind of close to plus for up to a certain size of arrays, and then plus is pretty good at kind of looking at the size of the array and then switching to specialized algorithms, which accelerate doesn't do. But basically, if you have these specialized cases, then it's nice. And the nice thing is basically that you can have for foreign function calls from accelerate. And we have that for stuff like fast Fourier transformation and so on, but where really fast solutions exist. Now, one thing you might have wondered about, which I completely ignored, about the type. So what is this stupid kind of ACK type constructor here? What does that mean? I said accelerate is an embedded language. So to be more precise, accelerate is a deeply embedded language. That means that while this dot product looks like it takes 2 arrays and produces a new array, what it actually does is it takes 2 abstract syntax trees which express computations which, once evaluated, produce an array and combines that to a new abstract syntax tree. So deeply embedded means that it's not just a simple library call, but we construct the abstract syntax tree, and then our implementation of accelerate takes this tree, basically does the optimization. So we're not relying on GHC optimizations, but these are kind of specific optimization. So this ACK type constructor basically expresses the fact that it's not a vector of A, but it's a computation that will result, once evaluated, in a vector. And consequently, this line below will not work because, well, show of this would print, if it were in the show class, would print the abstract syntax tree, which is probably not what you're expecting. So what we do need is call various version of the run function, which you can either get by importing the LLVM native backend, multicore CPU, or the GPU backend, and then you have various flavors of it. But you have to do that to generate the code and actually get some work done. So we have the collective parallel operations, which are denoted by this ACK type constructor, and then the exp denotes sequential operations. So this type of fold basically says fold takes as an argument a sequential operation and applies it in parallel. So one thing we prevent here with the type system is we can't feed, fold, or map already a parallel function, because otherwise we would have basically arbitrarily nested parallelism, which would be great, but which is really, really, really hard to map to concrete hardware. And I know that because I worked a lot with data parallel Haskell, we tried very hard to do that. And basically, it's hard. It's a really expressive programming model, which is really hard to map to architectures and especially to GPUs. So we restrict that. So to summarize, basically, when you have the Haskell program with accelerate, then you use GHC, you get your Haskell accelerate binary, and then at runtime of that binary, the AST basically is generated of your accelerate programs, compiled, optimized, compiled, then sent to the CPU, GPU, run there, and the result is copied back to Haskell. Now, I mentioned performance as one issue. And the problem there is, like, every program has this to worry about, like no matter in which language, but because we are working from a deeply embedded language where we do kind of just-in-time compilation, we also have to worry about the time it takes to optimize the accelerate program, to compile it, and to copy the result back to Haskell. Although, like in, for example, GPU stuff, you have to do that in some sense anyway. But we have to be conscious about these two things. And we are, so basically, when you use the same program multiple times, it only gets computed once, basically compiled once. So you pay for that only once. Then I said, our goal was to have a language that's convenient to use for Haskell programmers. So what does that mean in the context of a parallel, an embedded language? So it should feel, programming and accelerate, we want to make that it feels like almost like programming in Haskell. That means, and this is not a trivial issue, that none of the implementation details then leak to the program of accelerate. Even if you write a buggy accelerate program or an illegal accelerate program. Then another big issue for embedded languages are we really would like to have profiling and debugging, good profiling and debugging support. Profiling and debugging is already kind of maybe, not the greatest strength of Haskell anyway, but in an embedded language it's really hard, in a deeply embedded language, because for profiling, kind of matching the abstract syntax tree then to the generated code is doubly hard. And I'll talk about this later on. So in the embedding, one thing we have to do is we have to switch from regular Haskell values into values of the expression language, be it ACK or EXP, the thing is the same. And then at some point we have to switch back, and one way to do that we already saw, the run function. So let's focus on this part first. In my fold example, I never actually did anything to lift things into the expression language, right? I wrote just 0 and, just like I would write regular numbers. And the reason for that, of course, is that 0 kind of arithmetic operations, they are already overloaded. So I can just use that to conveniently overload numbers and arithmetic operations a bit more, and just say basically num an instant of num. And then num values now get automatically lifted into the language. So that's easy. But unfortunately, not all values are overloaded. So for bool, I can't do that trick so easily. Similarly for pairs, the pair time constructor. So here I can overload it that pair of 0, 4 is a pair of expression AB, but what I want is an expression of pair AB. So well, let's have a function that explicitly lifts a value into the expression language. And this is roughly the lift function this type. So E has to be a liftable type, and then it's lifted into, unfortunately not directly expression E, that would be easy, but we want the lift function to be able to lift it in any kind of in different levels, because you can have nested tuples, and then you don't want to, you want to have the lift function that can deal with expression in any nesting level. So plain is an associate type synonym, a function that basically maps this E type in some sense to strip all the expression things in it, so that we can use it for all depth levels of lifting we would want. Okay, so let's say we want to write the embedded version of this swap function then. So that it should have the type expression AB to expression BA. Now, if I look at the Haskell function, I of course use pattern matching. But can I use pattern matching in my swap on expression level? XAB is an abstract syntax tree that will eventually produce a pair, but it's not a pair yet. Right? So I can't use pattern matching directly. So one way to solve this is, well, I use I use the destructors for X and Y, and then I lift it. Yeah, not really. I mean, another thing which I probably should have mentioned also in this slide, why we like to use functional programming, is probably algebraic data types and pattern matching. And that's hard in a deeply embedded language. So, yeah, not great. Okay, so can we have an unlift function that basically takes this expression AB and gives me the pair? So basically kind of the other way back. Well, in general, the only way to get, in general, from XA to A is by evaluating it. But if my type A has only one type constructor, then I can actually do something, right? Because then I now already, let's say, if A is the unit type, well, then I don't have to evaluate it. I know the topmost type constructor is unit. Okay, that is boring. But for pairs it's the same, right? There's only one topmost type constructor. So if I have a value of type expression AB, I now, once it's evaluated, it will be evaluated to a pair. It will evaluate to a pair. So I can have this unlift function that, and this type is actually, it's a lot, it's simplified, the real type is worse. So it says basically something unliftable. You can kind of, if it is this in this class of types where I have a unique type constructor. And now I can write this function. I can basically call unlift here in the pattern to get xy and then lift it, kind of create the pattern yx and lift it. Not great, but yeah, kind of acceptable. But if we do that, this will happen. And you don't have to read it. You don't want to read it. You see a lot of plain and blah and basically like this tiny function and that big of an error message is bad. But what's worse is like a lot of the stuff like the plain and signature, a lot of implementation internal. So basically on the screen, and we really don't want the user to deal with that. So this was really the situation we had for quite a while, and I would say that it was one of the biggest hurdles we had for using it. Mm-hmm.
Good question. Whenever you
Yeah, so that's a good point. So accelerate, so the question is basically more or less whether accelerate is lazy or not, right? It is strict. So accelerate itself is strict. So when you have a pair, an expression of pairs, then both elements, both will be evaluated. It's a bit slightly more complicated. It's not completely strict, but yeah, more or less like this. So, okay, so this is really, and this was a big hurdle. Also, we used Accelerate for students in parallel programming. This is ugly. We can fix it with type annotations, basically, because the problem, as I forgot to mention, that the problem why we get this type message is that because we're using plain, this type function, basically the associated type class, the type checker can't resolve it anymore, what type you want. So you have to provide these type annotations. And as I said, so the fact that you have to add these type annotations, it's annoying, maybe not a drama. The drama, I think, is really that you see, like if you don't get it right, that you have these horrible error messages. But best thing is not to have that. Now, luckily, one nice solution for this is Haskell's bidirectional pattern synonyms. I guess most people will know what they are, but just if you don't, so if you have in Haskell kind of complicated patterns, for example, here I have a data type for calculation, and for binary ops, I parameterize it with the operator, and the operator can be plus, times, and so on. So simple addition is fairly long. Then I can say, well, make a pattern at E1, E2, which is a synonym for this pattern bin op app plus E1, E2. And then I can use now this type synonym, pattern synonym, add both to pattern match, so to deconstruct and to construct it. So I can, and here I can have much more complicated code. Not just kind of, it doesn't have to be a straight synonym. And we use that to, so we provide type pattern synonyms for tuples. Unfortunately, we can't overload them. So the nice thing really would be if we could give you pairs, and they look like regular pair type data constructors and patterns, but they're not. So that's not possible. So the compromise is basically, now they're called T2, T3, and so on, but you can do pattern matching. You don't have to worry about the type annotations and so on. Now, I said you can extend the ELT type with your own user-defined data types. And I think that is really important if we want to make the power of Haskell accessible in Accelerate. And we want to support product and some types. Also, like in general, in embedded languages, probably also recursive types. In the context of Accelerate, recursive types are not that important because they would be hard to, you usually don't have arrays of lists in high-performance computing. So that's not the main thing. So we need to solve three problems. It's basically, if you have a user-defined data type, how to map that efficiently to the target hardware, how to represent these in the AST, because in like our AST, the AST constructors of Accelerate is a fixed set we have in our Accelerate library, right? And now you add new type constructors. So we have to connect that to our basically closed language of existing constructors. And then we want to have pattern matching on user-defined data types in the embedded language. So how can we do that? And also it should happen without much overhead for the user, not only the user of the data type, but also the programmer who provides these data types. So for the mapping, we use Haskell generics to map arbitrary algebraic data types to uniform representation. So generics are basically, you can break all the algebraic data types down into recursion, sum, or product. Basically, it's alternatives, pairs, or recursion. And if you're happy with our default mapping, then this is being done for you automatically for your new data type. And also, we use generics to represent it internally, basically, in the Accelerate AST. For product types, the mapping is straightforward. So what we do is basically kind of the usual hoisting. So if you have arrays of pairs, then they get hoisted to pairs of arrays and so on. Some types are a bit more complicated, and there's more choice there, because if you have an array of some types, like do you have then 2 arrays and a flag vector, or 2 compressed arrays? So there's more choice there. Now, what you have to do as programmer to add your new data type now to the language and to get pattern matching on your new data type in Accelerate. So, for example, you add this type option. You have to add deriving generic, eld, and is tuple that has to do something with the internal representation. And then now for pattern matching, basically, we have to, if you have such a value of your new data type and we pattern match on it on the language, we have to, in the AST, generate the pattern matching code and the traces, and basically to how to figure out where pattern matching failed and so on. So that's the only point where we switch to template Haskell. You have to call this make pattern option, and that's all you have to do. And now you can write a function like this simple function, embedded function in Accelerate, which matches on your new option type. And again, you see that we have these constructors here, the patterns here. They look almost like the original ones, modular the underscore. So why do we have the underscore here? Well, we can't overload these existing, so none and some already exist in the program as regular type constructors, data constructors, and we can't reuse that. So our convention is we generate for you these patterns, your name, the name you chose, with the underscore. So I think this is a pretty kind of nice way, a fairly low overhead way to get this done. Mm-hmm. Sorry? We looked, yeah. So the question is whether we considered to use overloaded labels for that. I'm not sure if we look direct there. I think the problem there would be then to, I'm not sure if we could generate the code, because here, behind the scenes, a lot of code generation is going on. Like what the AST for this looks like is nothing like what you see here. And I don't think that's possible, but you have to think about that. So we didn't directly. So that's one thing, and this I mentioned Josh Merritt at the beginning of the talk. That was basically a lot of from this pattern matching stuff is from his idea, and I think it really improved the usability quite a bit. Another thing that I want to show you, and that's actually fairly recent work. The student just gave his thesis talk last week, but I think it's really interesting. So Accelerate comes by default and comes with a Tracy profiler. It's a C++ the profiler usually used for C++ for kind of graphics applications and things like that. But basically, because we are not profiling Haskell code, right? We're profiling the LLVM code we're generating if we profile an Accelerate program. But profiling in embedded languages is difficult because, well, you don't basically, the source code is not the Haskell source code, right? So making these connections is really hard. And then in Accelerate especially, you saw probably got an idea for some of the program transformations we're doing. We're doing fusion really aggressively. Stuff like sharing recovery, because it's a higher order embedding and we have to translate it into a first order embedding, things like that. So the AST changes completely. So connecting that to the generated LLVM code is hard. And yeah, so I said that. And Robert van der Helm, the master thesis student I mentioned, just wrote a really nice thesis, basically, on, in general, basically, allowing annotations in ASTs for embedded languages. Annotations for example, location, source code location, but also if you want to have local compiler optimizations. So for example, Accelerate uses fast math by default, but sometimes you don't want fast math because it makes floating point computations even less reliable than usual. So you want to switch that off, but not necessarily for the whole program, but for just some sub-computations. So his work basically gives a solution for that. So I just want to show you two screenshots. So that's kind of what Tracy output would look like. So the vertical bars are the different threads. The horizontal bars is over time, and then you see what the which thread is busy with what. And the picture basically colors and would have been the same before these annotations, but if you would have looked at basically what kind of kernel is executed, you would have gotten something like this top name, generate, blah, blah, and then a long hash thing. Now, we compile most of the code you have at some point to generate. So this does not tell you anything. But now, what it actually tells you, if you look at it, it says this generate, so that's this generate is the name of the kernel, and then it says, well, this is actually generated from the function zipwith, generate, zipwith, blah, blah, blah. So you also see which operations were fused together to get this kernel. And sorry, that's really, the resolution is really bad. And if you hover over the kernel, you see in the source code the line which produced this. So this makes a big difference, because for small programs, I mean, you can figure out what is what. For already something like Lulesh, it's really horror. Like, it's not fun to kind of debug profile a large Accelerate program if you have to reverse engineer where the compiler maybe got the code from that. So I think I'm really excited about this work. It's very cool. You have to, for all the functions you want to profile, you have to add the Haskell stack constraint, because we use the Haskell call stacks to kind of get the information from excessively. So that's, yeah, that is really overhead. But I think given that profiling for embedded languages is really a difficult thing, this is a relatively low overhead solution. So I'm very excited about the work. And as I said, it can also be used to fine-tune kind of optimizations and tell Accelerate things like, oh, I want this to be inlined. Or, for example, sometimes we don't fuse operations which are used multiple times, because in general that could lead to copying too much work. But most of the time, it's worthwhile for Fusion to copy work if you can fuse it then in more loops, because the number of memory accesses and the number of intermediate structures is still less. So, but usually a programmer knows better than the compiler, who always has to use some heuristics. So this will give people more actual control over Accelerate. So there's lots of work going on. Another thing is basically automatic derivation internally of uniqueness information, such that we can use internally destructive updates safely and address this problem I mentioned in the beginning, that for graph algorithms where you have these sparse updates, it's not great. Then another thing is, if you know languages like Halide or libraries like Halide, where you can the programmer can basically specify schedules, parallel schedules. At the moment, Accelerate usually just does a fairly good job at kind of producing a fairly good schedule, but again, it uses some heuristics, and if you, as a programmer, know better and want to convey some more information to the compiler, we want to make that possible. So Ivo and David are currently rewriting the complete backend compiler pipeline to make that possible. So also kind of more Fusion optimizations, more control over schedules. And then one thing, I forgot to mention that in the beginning, it was on the slide, but our GPU backend at the moment, unfortunately, is just for NVIDIA. And it would be great to have Metal backend, Vulkan backend. One fundamental problem is, for us, because it's an academic open source project, it's in some sense too easy. I mean, everyone knows that you can write another backend. You can't write a paper about it, but papers are the currency in which you are paid, and I can't ask a master thesis, can you write a new backend? And everyone, yes, of course it is possible. So this is a problem. And we're getting basically some money to some infrastructure work, but it's hard. So hackathon. I've got lots of ideas. If you want to be involved, so download Accelerate. If you want to play around with it, we would love to hear what you think, and we would love to you to have help us write new backends, or there's lots of stuff to do. Thank you for having me.
Thank you very much, Gabriel, for this talk. We have some time for questions. Yuri and me are running around with the microphones. Yuri? Okay, not yet. I'm going to just go in a breadth first search manner then. Where is it? Who had Arthur?
Hi, thanks for the great presentation. I wonder, does Accelerate have any abstractions for somewhat lower level things like global atomics, for example, so that you can carry some sort of state through the between the threads, or maybe shared data, like in GPU, shared memory, which is shared across threads within a block, some of these pieces?
No, so at the moment, really the way you're programming Accelerate is on a fairly high abstraction level. And as I mentioned, I would love to have more fine-grained control so that you can actually say something about these things if you have an idea of what you want to do with a particular schedule. But we don't have that at the moment. But yeah, to get from, it's nice because you get with fairly little extra work, pretty good performance to really, we actually want to compete with handwritten code. We need that.
Yes, and sorry, one more quick thing regarding fold operations. Do you have any type level enforcement of what sort of operations you can fold, for example, with this plus operation? that it's associative or something like that, because you accumulate them in arbitrary order?
Yeah, no, that's a good question, but no, we don't. So basically, the semantics you get for the fold is that you get a tree. Like it's deterministically a tree fold, and yeah, if it's not associative, then in most cases that might not be what you expect. But it has a clear semantics, but we don't. It's not. We don't do that. Other things. So there are things which also would be nice to enforce at the type level. Maybe, like for example, we check the shapes. So dimensionality rank, it's okay, but also these are not sized arrays. And you could also think about something where like if you do a zip with or a zip, then it just cuts off at the smallest one, just like a regular zip, but maybe you want something sized there. So that's another open research. That's actually research, and it would be practical to how can you do that, but no, we don't.
Next question.
Thank you, very interesting talk. My question is related to the first one. Basically, from the diagram you showed before, it looks like that every time that you have some result of computation on a GPU, let's say, you have to copy the result to CPU. So let's consider an example of inference for deep neural network. So how it works, basically you have a matrix multiplication, then you have like some nonlinear pointwise application, then you have another matrix multiplication, pointwise, and so on and so forth. So my question is it possible to execute all these commands on a GPU without copying the results to the CPU? And if it's not, when it will be possible? Thank you.
So it does not copy all the intermediate results all the time, basically, back. It tries to be fairly smart about when it copies things. But again, that's, I think, so I'm not sure exactly what kind of algorithm or heuristics it uses, but first of all, like the kernels, it tries to make the kernels fairly big as it can. And then also, if possible, it doesn't copy it back if it's not used in the user land before that. But yeah, also no explicit control over that.
Okay, thank you so much.
I have a question about the optimization and reification. 3 small questions. First, what is it contained in your benchmarks? Second, did I understand correctly that in one run of a program you have sharing between these and don't need to do it again, but if you run the program multiple times, you do it every time?
No. So basically you have different, I mentioned, you have different flavors of run. So one run, so just run takes basically an accelerate, so an ACC thing and runs it. So it would kind of, if you had dot product, then it would basically compile the actual arguments into the code and run it every time. That's usually not what you want. So you run n takes a function A to B simplified, an A, and runs it, and then it basically memorizes. So it realizes that you have that it has compiled it and does not recompile the code. Yeah. And then you have like a third flavor, run Q, which basically says if you really don't want to produce this at runtime, and you already know at Haskell compile time what the code is you want to have at runtime, then you can use run Q, and that generates it at Haskell runtime. At Haskell compile time.
Yeah, that was my third question. Thank you.
Yeah.
So 2 questions. First one, just kind of a shot in the dark. Have you considered how linear types could be useful to improve the implementation of the library, but still maintaining a type-safe API?
So I didn't get the first kind. What should we do with the types?
have you considered linear types as a way to improve the inner workings of the library while still keeping a type-safe API?
Yeah, so we with the verification work I'm doing, we're basically using a linearly typed language, and no, I don't want that on the surface. Like it makes things really, really hard. Okay. So I don't want that on the surface. What I want is basically, and what we're implementing at the moment is kind of a analysis which figures out basically what's used single time, but linear types, yeah, make like you pay a price for what you get.
And so, just out of
if I can say one more thing, basically, also like the linear types and Haskell linear types do something a bit different, right? Because they a promise about what a function does, and what we would need is kind of a promise about the values. So I don't think they would integrate very nicely into what we need would integrate very nicely into the Haskell type system. But I think we can get the benefits while shielding hopefully the users from the pain.
Okay. And so I was just also going to ask, does the implementation of the just-in-time compiler also use parallelism? Because there are two levels.
Yeah, no. No.
That was it. Thank you.
As you have data parallelism, you probably want to use it with floating point numbers at some point. And I'm wondering what is the support of Accelerate, for example, for directed rounding operations or floating point errors? Because I remember when I dealt with that it was particularly difficult with Haskell or functional programming in general.
We don't have a particularly good story about the floating point. We basically run it on the GPU, and which was when I was debugging this salt marsh simulation. Yeah, it's a pain. So that would be nice. Yeah.
We would have time for one last question. On the other side, great. Okay, let's do two.
So, do you have any implementation of deep learning primitives and maybe even like bigger networks and benchmarks comparing it to other frameworks?
So what we are working on at the moment is support for automatic differentiation. So basically on two things, a backend for an automatic differentiation library, and then general automatic differentiation in Accelerate, which, I mean, automatic differentiation is really very much at the core of that. And then some of the things we're trying to optimize for at the moment would be really useful for some of these operations. So the sparse updates would be good for some computations. Then one thing I talked to someone about is basically having these very large stencil kind of things. I think they are also quite frequently used in this context, and we don't have that implemented yet. So, yeah.
Is it possible to use template Haskell to do the support for case expressions and pattern matching? I mean,
yeah. So we use behind the scenes, this make pattern thing. That's a template Haskell that uses template Haskell. So without that, I don't think we couldn't figure out a solution without template Haskell to get all that done, because we need to kind of generate Haskell code so then you can use it.
Yeah, thank you.
Then let's thank the speaker again. Thank you very much, Gabriel.
Thank you.
Something small.
Thank you.
So, if I'm right, and the schedule has not been updated again, I guess the next talk will be the advanced track here at 1:30. Can someone correct me or verify this? 2:30 here. Good. In that case, enjoy lunch outside. There's some food trucks waiting, and see you later.